Okay, so now that we've introduced classes with data attributes and methods, we have the concepts and syntax that we need to talk about what are called linked data structures. And linked data structures include things like linked lists, both singly linked lists and doubly linked lists, also binary search trees and various other kinds of trees, stacks and queues, sets and maps, hash tables, or in general, what are called graphs. That is, a graph is a collection of nodes hooked together by arcs, or in the Python case, a collection of objects hooked together by references. All right, and so we can use classes in Python to implement these linked data structures. So a node in a linked data structure contains some data. This is one or more data attributes. And also the node contains links to other nodes in the same linked data structure. Now in Python, for these links, we use references. In other languages like C or C++, we would use pointers. So the internal representation of any linked data structure consists of a collection of these node objects containing data and links, references, pointers to other nodes. All right, so part of the state of some linked data structure object has to be a reference to the first node or the topmost node in this linked collection of nodes. If that reference to the first or topmost node in the linked data structure is none, that implies that the data structure is empty. So it would be possible for us, for example, to have a binary search tree object. The object is an object with state and behaviors, methods, but inside that object, the topmost node is going to be set to none, indicating that there are no nodes currently in that binary search tree. Okay. One of the benefits of a linked data structure, as opposed to some fixed size data structure, which actually in Python we don't really have fixed size data structures, but a linked data structure can contain arbitrary amounts of data, of course up to the limits of what your computer can actually store in memory. And the difference between different types of linked data structures is in terms of the performance that they offer and the amount of space that they require. So some data structures are better than others at sorting or searching operations, at insertion and deletion operations, at using more or less amount of memory, and so forth. To illustrate how we can implement a linked data structure in Python, we're going to take a look at what's called a singly linked list, which is the very simplest kind of linked data structure. Now, an advantage of a singly linked list is it can grow to be arbitrarily long within the limits of the amount of memory that you have. However, doing certain operations like sorting elements in a linked list or searching for elements in a linked list is going to be very slow. Inserting a value at the beginning of the list, on the other hand, is extremely fast. And deleting elements from within a linked list is also quite fast. All right, so let's turn this blabbering of mine into actual code. Here's a diagram of a singly linked list of values. This happens to have two values in it. First of all, this is our linked list object, our singly linked list object, and we've chosen the variable name s1 to keep track of this singly linked list object. The only state that we're going to keep track of within the singly linked list object is this data attribute called _first. If the list is empty, then _first is simply referring to none. In this particular example, though, on slide 5, first is referring to a singly linked list node containing two data attributes. The first data attribute is called _value, and for this first node, the _value refers to the stir object, the string object high. And the next data attribute, underscore next, I should be explicit about that, refers to the next node. Okay? That next node's underscore value is 12, and that next node's next node underscore next is none. So this is an example, this diagram is an example of a singly linked list of two values or two nodes. Notice that the values in Python in a singly linked list can be of arbitrary data type. So this singly linked list contains a stir as its first value and an int value 12 as its second value. Many other kinds of languages are more restrictive and typically require the items within a singly linked list to all be of the same data type. Okay, so to implement this in Python code, I've got a file, singly linked list.py, that's available for you on Canvas. We're defining a class, singly linked list, and the singly linked list is going to refer to some collection of nodes. Notice that I've created what's called a nested class within the singly linked, pardon me, try that again. I've created a nested class within this singly linked list class just to describe what each node contains. So I'm using this abbreviated name, SLL node, to keep track of what's within a node. This SLL node class does have a dunder init function, and because each node in a singly linked list contains both a value and a reference or pointer or whatever to the next item in the list, I'm being passed two parameters here, a value parameter and what I'm calling the next node parameter. Because this is a class method, of course, I'm using self as the very first argument, but that just gets passed around automatically. I don't have to do anything special to cause the value of self to be established. All right, so when the dunder init function is called and a value is passed in, then that value becomes the value of the underscore value data attribute within the SLL node. It's not necessary to pass a second argument because there's a default value here of none. If you do pass a second argument, then that argument, next node, becomes the value that the underscore next data attribute refers to. And if you don't pass that in, what you get is none by default. All right, so if you simply create a single node, then that single node's underscore next reference will be to none, indicating that that node does not refer to any following node. Here's a trivial remark that's nevertheless something to keep in mind. Notice that I've named this parameter next underscore node. And when you're looking at diagrams or looking at books about singly linked lists, the conventional name is just plain next. Python, unfortunately, well, I don't know whether it's unfortunate or not, but the fact of the matter is that in Python, next all by itself is a keyword. So I cannot use just plain old next as an attribute name or as a parameter name. Consequently, I've chosen to use next node as my parameter name, and I'm using underscore next as my data attribute name. Okay? So that's a trivial detail, but it's something that you do need to keep in mind. If you get yelled at while you're writing object-oriented code about next being illegal, well, it is. Next is a keyword, and you cannot use it as a variable name, as a parameter name, as a data attribute name. Okay, so my singly linked list class contains within it this private node class, and I also have an init function for the singly linked list class, which simply sets the _first data attribute to none. To none. All right? So what that means is that when I create a singly linked list object in my program, the singly linked list is initially going to be empty. It's going to be referring to no nodes at all. Let's take a look at some actual code using the singly linked list class. All right, so here is an application using the singly linked list class, and I'm calling this thing SLL_app. The singly linked list class is defined in a separate code file, a separate module, and so in my application program, I'm going to import that module using the abbreviation lowercase SLL. And now I'm going to invoke the class name with parentheses after it in order to create a singly linked list object. S1 is the variable being created here to refer to that newly created object. And of course, I have to use my module abbreviation with a dot in order to call that class to create an object of that class. All right. Diagrammatically, what's happened here in memory, approximately, is I have this variable S1 that's been created referring to this singly linked list. Oops, too much yellow. Okay. I've got this variable S1 that's been created referring to the singly linked list object, and internally that object has an _first data attribute referring to the first node in the singly linked list. But because the singly linked list is empty, _first at this point is referring to none. That's what's happening over here with this statement, self._first gets none. Okay, so we have our singly linked list class, which has a private internal class for the nodes that make up the linked list, and we have our dunder init function that establishes an empty singly linked list in which the first node is none. There is no first node. Let's now take a look at a method that will allow us to insert a value into our singly linked list. All right, the code for that is here on slide 8. So everything that we saw in the previous slide is still here, but now we're looking below that at this function called insert. And like any method, this has to take self as its first parameter. The second parameter is going to be the value that we want to have inserted into the list. Now, inserting always happens at the beginning of the list. And so the implementation of this insert function turns out to be remarkably simple, because what we're going to say is, let's modify this _first attribute to refer to a new SLL node containing the value that we've specified, and the next item, the _next item, should be the remainder of the list. Now, in this case, because the list is initially empty, when we insert our first value, that next item, this newly allocated node, is just going to refer to none. So notice that in order to insert a value into our list, that requires creating a new _SLL node, which is one of the members of the singly linked list class, with value as the first argument and the existing first node's reference as the reference to the remainder of the list. The reference to this newly created node will replace the value that was in the underscore first data attribute. All right, well, let's take a look at what's happening here in our application. So here, the application, we have added this insert line. Okay, here's our SLL app.py application. As before, we're starting out by creating an empty singly linked list object. S1 is referring to that empty singly linked list object. And when we say S1.insert 12, all right, so 12 is our value. We're going to create a new node with 12 as the value and with self.first as a pointer to the remainder of the list. Well, self.first, if we look back at our previous code, self.first was none. So that means that the underscore next attribute within this newly created node is going to be referring to that none. And the value in this newly created node is going to be referring to the int value 12. So that's all there is to doing an insert at the front of a list. It's a single assignment in which we are creating a new node, causing that new node to contain a value and a reference to what remains in the list. And the reference to this newly created node becomes the first node in the list. Okay? And so that's it. Now, if we do another insert, this time we're inserting a stir value high. Let's compare what we had on slide 9. So here's slide 9 where we inserted our first value into the list, which was underscore value of 12 underscore next, referring to none. All right, because each node contains these two data attributes. And when we now insert a string, notice that the node with underscore value referring to 12 and underscore next referring to none, that node still exists. There it is. But ahead of it, we have inserted another new node. This node has underscore value of referring to high and underscore next referring to what had been the first node. Okay, because when we're inserting, we're always putting our new node ahead of what had been the first node of the remainder of the singly linked list. Okay, and we can keep inserting more values at the front of the list by repeatedly calling s1.insert. So that's the insert function. We would like to be able to display the list that we have created. And we'll probably do that most of the time using the print function. Now, the print function automatically converts each of its arguments into a stir and then displays each of those stirs by default separated from each other with spaces. So our next job in implementing the singly linked list class is to define the $stir special method. Now, we, as the developers of the singly linked list class, can decide how we want to have this list displayed to the screen or converted to a string, which will then be displayed on the screen by the print function. And so our choice is going to be if the first node refers to none, that is, if the list is empty, we're simply going to return an empty string. All right, so when we convert an empty list into a string, what we're going to get is an empty string. Otherwise, we're going to construct this ret value. We're going to use this ret variable to keep track of the string that we're eventually going to return. And the first part of that ret string is simply going to be the first node's value converted to stir. Now, we need to do that conversion to stir explicitly because although in this particular case, the first value is a stir, so converting a stir to a stir doesn't really do anything. But notice that the next node has an int as its value. And so we definitely would need to convert that int into a stir in order to build up this stir representation of our singly linked list values. Okay, so we're going to start out by converting the first value in the list to a stir, and then we're going to use this loop variable underscore next as a reference to whatever the next node is in our singly linked list. Okay, so this is going to sound a little odd, but the first next node is going to be the next node following the first node in the list. Okay, so underscore next is going to get self dot underscore first dot underscore next. And while that next node reference is not none, that implies that there is yet another node whose value we need to append to our string. So if underscore next is not none, that is, if we're not at the end of our list yet, what we're going to do is to this ret value, we're going to append one space followed by the next node's value converted to a string. And then we're going to modify next to be the next node. When we eventually get to the end of the linked list, this underscore next loop variable will become equal to none. That means that we have reached the end of our linked list, and we simply want to drop out of the while loop and return this string that we have built up for this ret variable to refer to. Okay, so let's take a look at our actual string, our actual singly linked list example here on slide 10. When we get into this else part, because there are nodes in the list, when we get into the else part, ret is going to be set to underscore first dot underscore value, that is high, converted to a string. Well, converting a string to a string doesn't do anything, so ret is now equal to the string hi. Next is going to be set to first dot underscore next, which is this node, and that value is not none. That value is a reference to a node. So we are not at the end of our list yet. Consequently, we're going to modify ret. We're going to say ret has appended to it a space and the next value, which is 12, converted to stir. So we started out with ret containing the stir high, and now ret is going to be modified, and now ret is going to be modified to contain hi space 1, 2, all right? Because when we convert the integer 12 to a stir, we get the two characters 1 and 2. So we've got hi space 1, 2. Next is reset here. Next is modified to next.next. Well, next.next is none. We have reached the end of our list. This test at the top of the while loop fails. Hence, we drop past the while loop and we find ourselves at return of ret, and that's going to return this string of 5 characters, hi space 1, 2. All right, so let's see that used in our program. Here is a print statement added to our application program, and it does what I claim, okay? When we call print S1, internally, print automatically converts S1 to a stir. So print automatically invokes this dunder stir method on my singly linked list, which, as we've seen, converts the singly linked list into a 5-character string, HI space 1, 2, and hence that's what gets displayed on the screen. Okay, so we're making progress. We can now create an empty singly linked list. We can insert a value at the beginning of our singly linked list, and we can convert our singly linked list into a string representation, which we can then print or display on the user's screen. All right, so we're making progress. Let's take a look at another function now. In this one, we want to append a new value to the end of the list rather than inserting a value at the beginning of the list. And appending is going to be more complicated than inserting. Let's recall how easy insert was. For insert, all we had was a single assignment statement, and that was it. Because inserting always happens at the front of the list, and we know where the front of the list is, so we can just do our insert of our new node, and we're done. Appending is more difficult because appending is going to happen at the end of the list. Consequently, we need typically to use a loop to locate the end of the list before we can add our new node at the end of the list of values that's already in the list. So let's see how we can go about appending a value to our list. Okay, so we know that we're going to need a new node to append at the appropriate place. The first thing we're doing here is setting up this new node variable to refer to this newly created underscore SLL node with the value that's been passed in as the second parameter to the append method, and none to indicate that there will not be any more list after this value that we're appending. Okay? So we've got our node, and we have this variable new node referring to that node. If we append to an empty list, then appending to an empty list is effectively the same as inserting. That is, if we detect that self._first is none, we know that we simply want to append this newly allocated node at the beginning of the list. So we're going to say self.first gets the new node, and we're done. We're out of here. But let's suppose that _first is not none. That means that there are already nodes in the list, and we have to loop through the existing nodes to find the end of the list. This while loop is quite similar to what we already did in the dunder stir method. We're starting out by setting an underscore next variable to be a copy of the underscore first value. So underscore next is initially pointing at the very first item, the very first node in the list. And what we're doing here is we're testing whether there is a next. That is, we're detecting whether the node that we're currently referring to is the final node. Okay? But if there's a node after the node that we're currently referring to, then we need to move our underscore next reference one further along. So if there is a next node, that is, if the next is not equal to none, then we need to bump our next variable forward to next, And we keep going until we discover the node that is at the very end of the list. When we discover the node that is at the very end of the list, that is, when we discover that next is none, then it's at this point next that we want to add our new node. And now we're done. All right, so let's take a look at how this works from the application's perspective. Here is the first part of our application where we created the singly linked list object and we inserted, we inserted 12 first, and then we inserted high ahead of the 12, and then we printed the string representation of S1. So what we got out was HI space 1, 2. Now we are going to append 7 halves. Appending 7 halves means that we have to step through and locate the end of the list. Okay, the end of the list when there are just 2 nodes in it is this next data attribute. We modify that next data attribute to refer to this node containing, well, 7 halves is a float value, 3.5. And next is then none. But when we then do another append, that append also searches for the end of the list. The end of the list is now following this node containing a value of 3.5. And so we're going to append this new node whose value is the Boolean true, and X next refers to none. When we now print out the string representation of S1, what we're going to get out is HI space, 12 space for the int, 3.5 space for the float part, and then the word true for the bool true value. Notice something about this appending. Every time we do an append, it gets more and more expensive, because each time we do an append, we have to find the end of the list that is already there. So the cost of doing an append grows as the length of the list grows, whereas the cost of doing an insert remains constant. An insert is always just one step. It's just inserting the new node at the beginning of the list. Okay, now, we've done only the bare minimum. We have created methods for our singly linked lists so that we can create an empty list. We can insert values at the beginning of the list. We can append values at the end of the list. And we can convert the list into a stir, which we can then display using the print function. From our own experience with the built-in Python list type, we can imagine lots of other methods that we could add. We could add a method for counting the number of times that a value occurs in a list. We could add a method for deleting the first occurrence of a value in the list. We could develop a method for reversing the order of the nodes in a list. That one's rather tricky. Recursion is the easiest way to handle that one. We could extract a sublist, a copy of part of the list from an existing list. Pop would be to simply return the value from the front of the list and remove that from the list, and on and on. Now, most of these operations in terms of time performance are going to be order n operations because many of them have to scan through every single item that currently exists in the list, or on average, a lot of them have to look at half of the items. For example, if we're going to delete the first occurrence of some value, well, maybe if we're really lucky, that value occurs at the beginning of the list. If we're less lucky, it occurs at the end of the list. Likewise, contains. You know, on average, we're going to end up having to look at a big chunk of the list, even if we don't have to look at the entire list. So all of these, whether we have to look at the whole list or just half of the list or whatever, are order n algorithms. These two insert a value at the beginning of the list and pop a value from the beginning of the list are order 1 operations. So if that's all we're going to be doing with our singly linked list, and by the way, if this sounds like a stack, you're right. Inserting a value and then popping the value is really the same thing as pushing an item onto the stack and then popping that item from the stack. So if we're going to be using the singly linked list to implement a stack, then every operation that we do is going to be an order 1 operation, and so this is going to be an extremely efficient data structure to use for that purpose. Okay, so we've illustrated at the code level how to go about implementing a linked data structure. We usually have a class describing our linked data structure, and within that class we have a private class describing a node containing a data value within the linked data structure. We have methods for accessing and modifying the linked data structure, as well as for converting the data structure into a string representation that we can see on the screen. And we've talked about the idea that these various other operations that we can come up with do have performance behaviors associated with them. And what allows you to choose among different possible data structures is often based on these performance characteristics of the data structure. All right, so next up we'll look at binary search trees.